Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture number 31 of the course Stochastic Hydrology. In the last lecture, what we essentially did is to use the IDF relationships, intensity, duration, frequency relationships, and convert it into the design hydrographs. That was the first portion of the lecture, but in the subsequent part of the lecture, we introduced a new topic. This was to deal with multiple linear regression. So, starting with the simple linear regression, where we are relating one dependent variable y with one independent variable x in a linear form, y is equal to a x plus b. We extended that to relate one dependent variable y with several independent variables x 1, x 2, x 3 etcetera in a linear form. And we saw how to obtain the coefficients beta 1, beta 2 etcetera when we are expressing y as a function of x 1, x 2, x 3 etcetera with the coefficients defined as beta 1, beta 2 and so on. Towards the end of the lecture, I mentioned that the independent variables x 1, x 2, x 3 and so on in the multiple linear regression may be correlated among themselves, and also the number of variables that you may consider may be so large that the size of the problem itself becomes quite unmanageable in many realistic situations. And that is where we introduce the principal component analysis, where we will deal with a set of uncorrelated variables, and also we may use only a few of these uncorrelated variables, so that the size of the problem itself may reduce, and that is what is called as the principal component analysis. So, in today's lecture we will introduce the principal component analysis. So, this is what we covered in the last lecture. We discussed about the design hydrographs from IDF relationships, and then we introduced multiple linear regression. We also discussed a problem related with multiple linear regression. So, today we will start with principal component analysis. Now, before going to the principal component analysis, we need to revise a bit of matrix algebra. As you recall, two matrices can be multiplied if their sizes are compatible. What do I mean by compatibility? Let us say you have a n by p matrix and another p by q matrix. So, the number of columns of the first matrix equal to number of rows of the second matrix, then you can multiply two matrices. So, we get n by q in that particular example. We also know from your from our earlier matrix algebra that a square matrix has associated with it eigenvalues and eigenvectors. So, we will start with a revision of the eigenvectors and eigenvalues, which are necessary for discussing the principal component analysis. At least some of you would have gone through the matrix algebra earlier. When we say two matrices are can be multiplied, as I mentioned, let us say you have a n by p matrix and then you have a p by q matrix. When you multiply this, you will get a n by q matrix. The concept of eigenvectors is closely associated with the matrix multiplication. we say for a square matrix, that is if you have a n by n matrix, it can have eigenvectors. So, the eigenvectors are defined essentially for square matrix, and not all square matrices can have eigenvectors. So, some of the square matrices need not have eigenvectors. That is the second one. Second point, not all square matrices have eigenvectors. Now, what are these eigenvectors and how we determine etcetera, we will see presently. Then, if a n by n square matrix has a eigenvector, let us say that you are considering n by n square matrix. If it has eigenvectors, then it has exactly n eigenvectors. And associated with each of the eigenvector, you have n eigenvalues. So, if you have a n by n square matrix, you will have n eigenvectors and at most n distinct eigenvalues. So, how to determine these we will see today in today's class. It is also important for you to understand that the eigenvectors are orthogonal to each other, in the sense that they are perpendicular to each other. Remember that the vector indicates a direction. So, therefore, when you consider two eigenvectors, the eigenvectors will be normal to each other or orthogonal to each other. We will now see how we determine the eigenvalues and eigenvectors which are necessary for carrying out the principal component analysis. Just so that you do not lose sight of what we are discussing, the principal component analysis essentially we apply when you have to deal with multiple regression, where you are dealing with a large number of independent variables. So, typically let us say you are talking about hydrologic applications, where you want to estimate runoff at a particular location as a dependent variable, and it is dependent on several independent variables. Let us say rainfall it is dependent, and the area of the catchment it is dependent on. It is dependent on the soil moisture, it may be dependent on the humidity and temperature and so on. So, you want to relate the runoff at a particular location with all the independent variables. Now, these independent variables that you are talking about may have a correlation among themselves, in the sense that one variable may be dependent on the other, but we are still calling them as independent in as much as they are not dependent on y or the runoff in this particular case. For example, your soil moisture may be related with rainfall, and rainfall and soil moisture together are considered in the regression equation. So, to account for the correlations among the independent variables, or actually to remove the correlations among the independent variables and form another set of variables which are uncorrelated with each other, and to possibly reduce the size of the problem itself. What I mean by that is, let us say you had 10 variables, y is equal to y is a function of x1, x2, x3 etcetera, 10 variables, and each of the 10 variables has 50 years of data, and monthly data is what you are considering. So, each of the variables has 600 values. So, the problem dimension is 10 into 600. Now, that may become slightly unwieldy, and therefore, to remove the correlations among the independent variables and to possibly reduce the size of the problem, we carry out the principal component analysis. And especially when you are dealing with the climate change impacts on hydrology, towards the end of the lecture, towards the end of this course, I will give one lecture on how do we handle the scaling issues when we are dealing with climate change impacts. There it will become much more clear on where we use the principal component analysis. Especially when you are dealing with the scaling issues in the climate change impacts, you deal with large number of climate variables, and therefore, it is important for us to reduce the size of the problem and also to address the problem of correlations among the independent variables, and that is what we do in the principal component analysis. Okay, so let us start with the basics of the principal component analysis. What does it do actually? It is a way of identifying patterns in the data. You have 10 variables, all of the 10 variables you have measured, and you have the observed data on all of the 10 variables. So, there is a huge amount of data that is available to you. The underlying pattern in this data set is what is captured by the principal component analysis. So, PCA is a way of identifying the underlying patterns in the data, and then once we identify the patterns, we express this data in such a way that the similarities among the data and the differences among them are highlighted in some sense. And once the pattern is found in the data can be compressed without losing too much of information. What do I mean by that? Let us say that in the pattern of the data, you see that some components in some sense, which we will see presently, some components are much more predominant in their information content compared to other components. Then you can only focus on these particular components, which are much more predominant in their information content, and that is what we mean by the data can be compressed. In fact, in image analysis etc., the image compression uses principal component analysis in several situations. Now, this will require a bit of background on matrix algebra. So, we will just quickly go through some preliminaries of the matrix algebra, especially how we obtain the eigenvectors and the eigenvalues. So, first let us define what is a eigenvector and a eigenvalue. Let us say A is a square matrix and lambda is a scalar, and x is a non-zero column vector satisfying A x is equal to lambda into x. So, let me demonstrate that. That is, we have A as a square matrix and this is a column vector, lambda is a scalar and this is a column vector. Now, this column vector x is a eigenvector of A, and lambda is an eigenvalue of A. That is, if you can find a vector x which satisfies this A x is equal to lambda x with lambda as a scalar and x being a column vector, if you can find such a vector, then it is called as an eigenvector of A, and the associated value lambda is called as eigenvalue of A. Now, as I mentioned earlier, eigenvectors are possible only for square matrices, and the eigenvectors x are orthogonal to each other. Let us say you had two eigenvectors, then both of them will be normal to each other. Vector denotes a direction, and therefore, when you can talk about the direction of a vector, and the two eigenvectors will be orthogonal to each other or normal to each other. Then lambda is an eigenvalue of n by n matrix A with corresponding eigenvector x. So, each of the eigenvector is associated with a eigenvalue lambda. Look at this now, A x is equal to lambda x. This is how you define your eigenvector x. Now, if I write A minus lambda I into x is equal to 0 with x not equal to 0, this leads to the determinant A minus lambda I is equal to 0, and this is how we determine the values lambda. That is, if A minus lambda I into x is equal to 0, you can either have x is equal to 0 or A minus lambda I equal to 0, but we are saying that x is not equal to 0 because you are stating that eigenvectors exist, and therefore, you will get A minus lambda I, the determinant of that must be equal to 0. This is how we determine the lambda or the eigenvalues. As you can see here, this is the n by n matrix, A is a n by n matrix, and therefore, you may get a maximum of n distinct eigenvalues of A. You may have n values, but some of them may be equal to each other, and therefore, you will get maximum of n distinct eigenvalues of A. So, these are the two important things that you must remember. One is you will determine the eigenvector x by this expression A x is equal to lambda x, and the other one is that you will determine the eigenvalues A minus lambda I is equal to 0, the determinant of the A minus lambda I is equal to 0, and that is how you determine the eigenvalues lambda. Any given square matrix, first you determine the eigenvalues, then use the eigenvalues in this expression to get the eigenvectors. So, let us look at one simple example now. Let us say you take a square matrix A 1 2 2 1, very simple matrix. We will first obtain the eigenvalues. So, A minus lambda I, this is the identity matrix I. So, A minus lambda I, determinant of that is equal to 0. So, we will get 1 minus lambda, I am picking up from here 1 minus lambda and 2, 2 and 1 minus lambda. That is how you form the A minus lambda I. I is a unit matrix, remember 1 0 0 1 in this particular case. So, from here this is the determinant. So, I can form an expression for lambda, this is equal to 0. So, I will get this as 1 minus lambda into 1 minus lambda minus 4 is equal to 0, or you get the expression lambda square minus 2 lambda minus 3 is equal to 0 from here, and when you solve this is a quadratic. So, when you solve this you get two solutions, lambda is equal to 3 or lambda is equal to minus 1, both of these satisfy this expression, and these are the eigenvalues for the matrix A. So, the eigenvalues are 3 and minus 1 for the matrix A. You had a 2 by 2 matrix, therefore, maximum of 2 eigenvalues are possible, and that these are the 2 values that you obtain. In some situations, when you have 2 by 2 matrix, for example, you may get both of them equal to each other, in which case there is only one eigenvalue. So, there are maximum of n distinct eigenvalues possible for a square matrix of the size n by n, and always you obtain the eigenvalues first and use the eigenvalues to obtain the eigenvectors. So, we will now obtain the eigenvectors once you have found eigenvalues. Remember, corresponding to each of the eigenvectors there is a eigenvalue, or they come in pairs, eigenvalues and the eigenvectors they come in pairs. So, you have through 2 lambda values, and corresponding to each of these lambda values we must find one eigenvector now. The eigenvectors are obtained by A minus lambda I into x is equal to 0. These are matrices A minus lambda I into x is equal to 0, and I specify the lambda value to obtain the value of x. So, I had 2 values of lambda. So, I will first start with lambda 1 is equal to 3 and substitute lambda 1 is equal to 3 in A minus lambda 1 I into x 1 is equal to 0. I is a unit vector, and therefore, from this A here, which is 1 2 2 1, I will get 1 minus 3 2 2 1 minus 3, because lambda is 3. I am putting lambda 1 into I is a unit matrix, and I will write this x 1 as x 1 y 1. This is the eigenvector now. So, I will get this as minus 2 2 2 minus 2, and this leads to two equations, minus 2 x 1 plus 2 y 1 is equal to 0, 2 x 1 minus 2 y 1 is equal to 0. The equations that you get out of solution of these are identical. For example, you can multiply this with minus 1. So, you will get 2 x 1 minus 2 y 1, which is identical to this. So, from this I can write x 1 is equal to minus y 1. I am sorry, you can write x 1 is equal to y 1 here, and for any chosen x 1 arbitrary, you can choose x 1 arbitrary, you can get the eigenvector x 1 y 1. Your eigenvector was x 1 y 1 and the solution is x 1 is equal to y 1. So, any chosen x 1, you will get the corresponding y 1 as x 1 is equal to y, as y 1 is equal to x 1, and therefore, you will get the eigenvectors. So, the eigenvectors corresponding to the eigenvalue lambda 1 is equal to 3 are the vectors x 1 y 1 with x 1 not equal to 0, because that is what we have specified earlier. For example, if you take x 1 is equal to 2, as I said, any arbitrary value of x 1 satisfying x 1 is equal to y 1 will define your eigenvectors. So, if you take x 1 is equal to 2, y 1 is equal to 2, then the eigenvector is 2, 2 corresponding to the eigenvalue lambda 1 is equal to 3. So, like this you can form several eigenvectors. Now, we will take the other lambda 1, which is lambda 1 is equal to minus 1. If you put lambda 1 is equal to minus 1, I will get 2 and 2. Remember, your A is this matrix 1 2 2 1. So, I am saying 1 minus 1, that is minus of minus 1, which will be plus 2, and here 1 minus minus 1, that will be again 2. So, this is how you get 2 2 2 2 x 2 y 2. This x 2, which is a vector, I will write it as x 2 y 2, and you will get the equation 2 x 2 plus 2 y 2 is equal to 0, which is identical to the second one. This has a solution x 2 is equal to minus y 2. So, you can choose x 2 arbitrarily and then you get y 2, and you will get the vector here x 2 minus y 2. So, the eigenvectors corresponding to lambda 2 is equal to minus 1 are, these are the vectors. You can choose any value of x 2 and set x 2 is equal to minus y 2, and that is how you get with x 2 not equal to 0. So, this is how you obtain the eigenvectors and the eigenvalues. As I mentioned, given any square matrix, if you want to determine the eigenvectors, first you find the eigenvalues by taking determinant A minus lambda I, that determinant equal to 0. A is a square matrix and I is a unit matrix. You will get at most n distinct lambda values for a square matrix of size n by n. Use these n distinct lambda values to obtain the corresponding eigenvectors. How do we get this? That will be A x is equal to lambda into x, and x is the eigenvector. So, corresponding to each of the lambda values, you get one eigenvector, and eigenvectors and eigenvalues come in pairs. So, we will use this method of obtaining the eigenvectors and eigenvalues when we go to the principal component analysis. So, let us see what we do in the principal component analysis now. As I mentioned, you have several variables, and on each of the variables you have the data available to you. Let us say that you have, as I mentioned earlier, you have variables such as rainfall, soil moisture, temperature, humidity, and so on. And so, you have several such variables, and your dependent variable may be run off at a particular location, and you have the data, observed data on each of these variables. So, you have data on p variables, and these some among these may be correlated. Let us say rainfall may be related with temperature in some sense, or the soil moisture is related with rainfall, and evapotranspiration is related with both soil moisture as well as temperature. So, there may be significant correlations among the several variables. Now, what do we mean by correlation? If you recall from your earlier lectures on this course, correlation actually means that there is a common information, there is a information contained in one variable is also contained in some other variable, and this information we have to filter out, so that we do not repeat what is contained in several variables. So, the PCA or the principal component analysis, in some of the textbooks you will also see this is called as principal components analysis, but they are analogous. So, the PCA actually transforms the P original correlated variables into P uncorrelated components. These are called as principal components, or they are also called as orthogonal components, in as much as they are orthogonal to each other. They are vectors, and therefore, they are all orthogonal to each other. Now, these components are actually linear functions of the original variables. So, you do a linear transformation of the original variables into some orthogonal axis. So, you are actually transforming the original data into some orthogonal components, and these are linear transformations. Let us say we write the transformation as z is equal to x into a. Now, x is your n by p matrix of n observations on p variables. Will not lose sight of what we are doing here. So, we will just go through our hydrology example. Let us say I have three variables. One is rainfall, another is runoff, and another is let us say soil moisture. You have three such variables. On each of these variables, so these are the variables. On each of these variables, you have number of observations. Let us say you have 1, 2, 3 etcetera, you have n number of observations. If you have 50 years of monthly data, n will be 600. So, this is p and this is n. So, the x vector, which is x matrix, which is a matrix of the observed data, will have a size of n by p, and that is what I am writing here. So, this is x is n by p matrix of n observations on p variables, and now z is a n by p matrix of n values for each of the p components. Now, A is our matrix of components. First, let us look at A. You had p variables, let us say you had 3 variables, then p is equal to 3. Now, A is a 3 by 3 matrix of coefficients defining the linear transformation. This is in fact the principal components, and Z is the transformed data. So, from the original data, on the original data you apply the principal components to get the transformed data, and that is a Z matrix. Now, when we are doing the analysis, we take the X matrix as a deviation matrix. That means, from the observed data you deduct the mean, and many times you divide it by standard deviation also to form the X matrix, and A is the matrix of p coefficients, p by p coefficients, which we will see how to obtain this now. and Z will give you the transformed data. So, this is what we essentially do in principal component analysis. Okay. So, how do we do the principal component analysis? We have n observations on p variables, we start with that data. In fact, you relate this with what we discussed in the multiple linear regression. You have observations corresponding to each of the variables, and there is a dependent variable, there are large number of independent variables. Now, from this matrix of n observations on p variables, you form a matrix of size n by p with deviations from mean for each of the variables. Now, typically we do this on the independent variables. So, you pick up all the independent variables and then deduct their mean and formulate a matrix of size n by p. Then this is a n by p matrix. So, we can obtain the covariance matrix. There are p variables. So, we also obtain a p by p covariance matrix, that is correlation of variable x 1 with x 2, x 1 with x 3 and so on, x 1 with x p, similarly x p with x 1, x p with x 2 and so on. So, you get a covariance matrix of p by p. Now, this is a square matrix. So, we can obtain the eigenvectors and eigenvalues for this square matrix. So, we obtain the eigenvectors and eigenvalues for this covariance matrix. This is a p by p matrix, therefore, we can get p eigenvectors and at most p distinct eigenvalues. From these p eigenvectors, we can choose some eigenvectors for further analysis using regression, depending on how important they are in terms of the information content on the dependent variable. We will come to that slightly later, but from these eigenvectors we pick up some of the eigenvectors which we call it as principal components, and use this expression z is equal to x into a to obtain the transformed data set. So, this is what we do. I will just quickly go through it. We start with the data and then the data we convert it into a n by p matrix with deviations from the mean x minus x bar, and in some cases we take x minus x bar by sigma or x minus x bar by s, where you are standardizing. Why is standardizing necessary? Because you may have several variables all with different units. For example, I may be dealing with one of the variables as rainfall in millimeters, area in hectares, then soil moisture in millimeters per centimeter or percentage and so on. So, these units are all different and therefore, it is advantageous to standardize them. By standardizing, I mean x minus x bar by s. You deduct the mean and divide by the standard deviation. Then we get corresponding to each of the variables, you take the covariance with respect to the other variable. Remember, covariance you take with one variable with the other variable x into y, the covariance of x with y, covariance of x with z and so on. Covariance of x with itself is the variance. So, we get this covariance matrix of size p by p. Because it is a square matrix, we take the eigenvectors and eigenvalues of these and then define the principal components corresponding to the eigenvectors and eigenvalues and obtain the new data set. So, from the original observed data set of n by p, now we obtain another data set still of the same size n by p, and the new data set is in terms of the principal components and they are all uncorrelated, they are all the different principal components are orthogonal to each other. So, this is how we transform the original data set into a new data set, where you are dealing with uncorrelated variables and you are dealing with orthogonal vectors. We will take a simple example now to demonstrate this procedure. We are not right now worried about which is dependent and which is independent variable for this particular exercise. We are taking two variables, rainfall and runoff. So, your P is equal to 2 and you have data for 15 years. So, these are 15 values now. The mean of rainfall as you obtain from here is 108.5 centimeters and the mean of runoff is 38.3 centimeters. So, with this now we will come see how we obtain the principal components. First you look at this data 105, 115, 103, 94 etcetera, it goes on up to 85. Similarly, for runoff it starts with 42, 46 and so on. So, this is the original matrix of data. P is 2, this is rainfall, this is runoff and N is 15. There are 15 observations each available for the two variables. Now, I form a matrix X by deducting mean of rainfall from this column and the mean of runoff from this column. Mean of rainfall is 108.5, mean of runoff is 38.3. So, 105 minus 108.5, so, I will round it off minus 1.3, similarly 3.4 and so on. So, this is how I form the matrix X. Now, X is simply X minus X bar, that is here I am taking X minus X bar, where X is the original data and X bar is the mean, both for your rainfall as well as runoff, and that is how you obtain your values 1.3, 3.4 and so on. So, once you formulate the matrix X, we will also calculate the covariance matrix. There are two variables x y and x y here. So, let us say if I write x comma y, recall from your earlier lectures, I am dealing with random variables here. So, let us write capitals x and y. So, I will take a covariance and the covariance matrix is formed by covariance of x comma x here and x comma y, y comma x and y comma y, and the covariance between two variables is obtained as sigma x I minus x bar y I minus y bar divided by n minus 1, where n is the number of data 15 in this particular case, and x I is from your table here, this is x I, this is y I, like this it goes. So, that is how you calculate the covariance matrix, and these are the values as you obtain from there. You can do it as an exercise. You will get covariance is 216.67, 141.35 and x y is the same as y x, and you will get these covariance matrix. This is a square matrix. So, let us obtain the eigenvectors and eigenvalues corresponding to this matrix now, covariance matrix. So, how do I get the eigenvectors? Remember, whenever you have a square matrix, to get the eigenvectors, first you obtain the eigenvalues. So, this is the A matrix, let us say, which is a covariance matrix as we obtained just now. We use determinant A minus lambda I is equal to 0. So, A minus lambda into this is a unit matrix is equal to 0. You will get lambda 1 is equal to 322.4 and lambda 2 is equal to 27.7. One of the lambda values is significantly higher compared to the other lambda value. We will see what is the significance of this, what is the implication of this when we do the regression using the principal components. We use these lambda values, and like I did in the example, corresponding to each of the lambda values you get a eigenvector. So, I will get the matrix of eigenvectors 0.801, 0.599 is one eigenvector and minus 0.599 and 0.801 is another eigenvector. Remember, these eigenvectors are unit vectors in the sense that let us take the distance of the eigenvector indicated by the eigenvector, that is this is one eigenvector. So, I will take square root of 0.801 square plus 0.599 square, this is equal to 1. So, generally any program, if you use MATLAB etcetera and ask for eigenvectors, it returns unit vectors, unit eigenvectors, and by unit you recall that we mean the distance given by the vector is 1. Similarly, you can see that the distance given by this is also equal to 1. So, starting with your original data, first you transform the original data into a data consisting of deviations from the mean, and then you also formulated the covariance matrix, and this is the covariance matrix here. Covariance matrix is a square matrix of size p by p, p is equal to 2 here because you are dealing with 2 variables. Once you get the covariance matrix, you get the eigenvalues of the covariance matrix. Because it is a size 2 by 2, you will get 2 eigenvalues in general. So, lambda 1 is equal to 322.4 and lambda 2 is equal to 27.7. You obtain the eigenvalues, go to the eigenvectors equation, a minus lambda x is equal to 0. From this you get x, because lambda is given. So, first you put lambda 1 is equal to 322.4, you will get one eigenvector, and lambda 2 is equal to 27.7 you get, and you get the other eigenvector, and you form the matrix of eigenvectors. And these eigenvectors are unit vectors. Now, I just mentioned about the relative magnitudes of the eigenvalues. One is 322.4, another is 27.7. These have an implication on how we choose the principal components, how many of the principal components we choose. The eigenvectors corresponding to each of the lambda values, they explain the original variance to certain degree, which is related to the eigenvalues. What do I mean by explain? That is, so much of variance has been contributed by this particular eigenvector, is what I mean by explaining the variance. Let us say you are talking about runoff as a function of rainfall, and then you obtain as a function of rainfall and another variable soil moisture, let us say, and you obtain the eigenvectors corresponding to each of these, that is you get 2 eigenvectors. The first eigenvector may explain 95% of the variance in the runoff, whereas the second one may explain only 5%, which means you can afford to ignore the second one. And therefore, you look at how much of the variance in the dependent variable is in fact explained by each of these different eigenvectors. And how do we do that? We compute or calculate the trace of S, where trace of S is defined by simply summation of lambda j's. You got the eigenvalues. So, add all the eigenvalues and that will define your trace of S. And the fraction of the total variance accounted for by the jth principal component is lambda j by trace j. Simply you get lambda j by trace j, that will give you the amount of variance that is explained by that particular principal component. Okay. So, in this particular case, let us say lambda 1 is you have 322.3 and this trace S comes out to be 350.1, 350.1. So, the first component, first principal component lambda 1 explains 92% of the variance, 0.92 fraction, which is 92% of the total variance is explained by the first principal component, and the remaining 8% is represented by the second component. Remember, the identity of the original variables namely runoff and rainfall and runoff is gone now. We are only dealing with the principal components, and principal components are a linear combination of both the variables. So, you cannot relate lambda 1 to be runoff, lambda 2 to be or lambda 1 to be rainfall and lambda 2 to be runoff and so on. The original identity is gone. We are simply dealing with some transformed variables lambda 1, lambda 2, which are the eigenvalues, and the eigenvectors in fact, which define the principal components. We are dealing with the principal components. And therefore, in this particular case, you can afford to ignore the second principal component if you are dealing with a regression relationship, which we will come to presently. So, this is how you carry out the principal component analysis. First, transform the data into a data consisting of deviations, so that you are centering the data in some sense, and if you have variables with different units, you also standardize them and then formulate the matrix, matrix X consisting of the transformed data. Then you form the covariance matrix. Corresponding to the covariance matrix, you obtain the eigenvectors and eigenvalues and look at how much of variance has been explained, or how much of these how much of the variance is contributed by each of the eigenvectors, and that is the objective of the principal component analysis. So, you form the principal components in terms of the eigenvectors and then look at how much of this information is coming from each of the principal components. What is the purpose of doing all this? We had a set of large number of variables, and then we want to fit a regression relationship between a dependent variable and a number of independent variables. And we carry out the principal component analysis on the independent variables x 1, x 2, x 3, etcetera, up to x p. There are p independent variables. We carry out the principal component analysis. We know, let us say you had p variables, you get the p principal components or p eigenvectors, and we know each of these eigenvectors or the principal components, their contribution to the variance in the dependent variable, and we choose only those particular components, only those principal components which are contributing significantly to the variance in the dependent variable, and that is what we do in regression using the principal components. So, we know now how to carry out the principal components. We use this principal component analysis to do the regression. So, we had the original regression. From the original regression, we are going on to regression with the principal components. Let us see how we do this. So, to continue the example now, as I mentioned, we said 92% of the variance is explained by the first component. So, we will neglect, for the time being, we will neglect the second component. So, we will take only the first eigenvector and call it as the feature vector. So, we call it as the feature vector, we are choosing only the first one. You can choose both of them as feature vectors. So, feature vectors are those eigenvectors which are chosen for the further analysis. So, this feature vector now is 0.801, 0.599 corresponding to your first eigenvector. Then with this now we obtain the new data set. This was your original data set minus 1.3, 3.4, that is by original I mean these are the data sets that you use for the analysis. This is x and this is your A. These are the data sets formed with the deviations from the mean, and this is A, and you will get Z as the new data set. What has happened now? The original P by N matrix has been converted into 1 by n matrix. So, this is the transformed data. So, if you had 10 variables, you would have had 10 by n matrix, and if you choose only one eigenvector, then you would still get 1 by n, which means the remaining 9 you would have discarded, in the sense that they are not contributing so much to the variance, or the first component alone is able to explain most of the variance, or the first component alone is contributing to most of the information content in the data set, and therefore, you discard the other principal components and then deal with only this data set. Let us say we did not ignore the second one, and still we want to use the second eigenvector also, in which case we can choose, this is 2 by n matrix and n is 15 here. I am sorry, I have taken 10 values here. So, n is 10 here, and then this is the 2 by 2 eigen matrix. This is one eigenvector, this is another eigenvector, and so you will get 2 by 10. So, this is the transformed data. So, like this, from the original data you use the eigenvectors to get the transformed data. Then we come to the question of regression using principal components. So, let us quickly recall what we did in this example now. In this example, what I have done is I have chosen only the 10 values here and then carried out the exercise. I have gone up to 79 and 20. So, remember I have used only 10 values here. So, the same thing can be done with the remaining with the complete data set 15 values. So, these are 10 values and then I get a transformed data of the remaining 10 values. So, from the two independent variables, let us say that your independent variables were rainfall and runoff for some purpose. From the two independent variables, you have got one data set now, which are all principal components. These are all called as the principal components. This is a eigenvector, and in fact, this is called as a principal component, which has a size of 1 by 10. So, this is the principal component that we are talking about. We can use this information because we know now that this principal component contributes to 92% of the variance in the data set. So, we can discard the other and then simply use this data set. In the multiple linear regression expression, we will come back to that topic now. In the multiple linear regression, you had several variables x 1, x 2, x 3 etcetera. There are p variables, you get p principal components, and p in principal components, you know the contribution of each of these principal components to the variance of the dependent variable y. Let me quickly tell what I mean by that. Let us say you have y is equal to, you want to write it as a function of x 1, x 2 etcetera x p, p variables, and therefore, you get p principal components. And each of these p principal components, the contribution to the variance in y or the variance in this particular data set can be obtained like we did in the example here. We got 92%. So, each of the principal components you can obtain what is the contribution to the variance. Then depending on that, you can choose q of them less than p to be included in the regression equation. Let us say I choose only 2, if 2 of them can together explain about 95% of the variance in y, and so on. And then using only those two, we fit the regression relationship not on the original data, but now on the principal components. So, we have obtained the principal components, now you regress the dependent variable y with respect to the principal components, and that is what we do in the next lecture. So, we will see how we take this principal component analysis forward and then apply them in regression, where we are relating the dependent variable not with respect to the original variables, but with respect to the principal components. And remember, principal components are a linear combination of the original variables themselves, and therefore, individual principal component does not indicate any particular physical variable that we considered earlier. For example, principal component number 1 does not indicate rainfall. It is some linear combination of rainfall and runoff both together in that particular example that I talked about. So, the regression that we develop now, y as a function of principal component number 1, principal component number 2 and so on. We may have chosen q number of principal components with q being less than or equal to p, will be a new regression relationship now. And what is the advantage that this has? This is now dealing with all uncorrelated variables, because all the principal components are uncorrelated with each other, and it has also compressed the original data set in the sense that we are not choosing all the p principal components, but we are choosing some lesser number of principal components compared to the original number of variables. So, we will summarize now. So, we started with how to compute the eigenvectors and eigenvalues for a matrix. The eigenvectors are computed only for square matrices. Eigenvectors are defined for square matrices, and to determine the eigenvectors, you first determine eigenvalues. Eigenvalues are determined by determinant A minus lambda I is equal to 0, where A is the square matrix and I is the unit matrix. And then once you get the lambda associated with each of the lambda values, you have an eigenvector. You will get the eigenvector as A x is equal to lambda x, where x is the eigenvector. Then we went on to principal component analysis, where we define the principal components as the eigenvectors in fact of the covariance matrices of p variables. So, you have a size of p by p, and that is how we get the eigenvectors. These eigenvectors are in fact the principal components. So, we also know how much of the variance is contributed by each of the eigenvectors. Depending on the contribution to the variance, we choose a few of them, eigenvectors to use in regression. So, in the next lecture then we will start with regression using the principal components. So, we have arrived at the principal components starting with the original data. We will use the principal components in the regression and see what is the information that we can derive out of that, and what are the advantages arising thereof. Thank you for your attention. We will continue the discussion next time.